Hi, everybody. So I wanted to record a little supplement on another isolated topic that will come up again, and that is about the Fourier transform of a periodic signal. So let's say that we have a signal that repeats itself in some kind of waveform. Okay, and so on. Okay, now, if we think about, our interpretation of the Fourier transform as being a way of constructing a signal out of sinusoids of different frequencies, well, let's think about what that means in this case. So let's say one period of this signal is about that long. And even though I haven't drawn it so well, let's say that that's consistent in the waveform within each period of this repeating waveform is consistent, okay? So think about what that means for the sinusoids we would use to construct this. If the waveform has to be the same, in every period, then we really have to have sinusoids that complete an integer number of cycles within this time period. Oh, there, that happened again. Okay. So that would be one of them. Another one might be one that completes 2 cycles in that time period. 1, 2, and another one, might be one that completes 3 cycles in that period. 1, 2, 3. Okay, and so on. We could have more of those. Now, the reason why this is significant and that it really has to be constructed only of these sinusoids is that if we had a sinusoid that didn't complete an integer number of cycles in that period, let me try orange here. So let's say we had one contributing to this that kind of went like that. Then there's no way for the waveform in the next cycle to be identical to the waveform in this cycle if this thing varies like this, because if this contributes, with any magnitude at all to this signal, then we're going to see this kind of drift happen, and there's going to be, the waveform will be at least slightly different in this period and the next one. So in order to construct a waveform, oh, I do not know what happened there. In order to construct a waveform where we get identical waveforms in every period, we need to only use frequencies that complete an integer number of cycles within the periodicity of our signal. So here's the thing. Periodic signals can only use Fourier sinusoids that complete an integer number of cycles in one period. Okay, so that says if I have a periodic signal and I take its Fourier transform, only certain frequencies in the Fourier space are going to be contributing. Other ones are going to be 0. Or if it's not perfectly periodic, but nearly so, you might get contributions at others, but it'll certainly be dominated by the ones that meet that condition. Okay, so, right, one period of the periodic signal. So this guy, the blue one, generally we would refer to as the fundamental frequency. And basically it has the same period as the original signal. Right, so if the original signal repeats every 1 millisecond, this is a sinusoid that basically its period is 1 millisecond. These and any others, that are integers, we refer to as harmonics. And so they will go as 1/2 the period, twice the frequency, one-third the period, 3 times the frequency, and so on. Okay, and those are the only things we can have. So there's a fundamental and harmonics. Okay, now let's look at an example. Over on MATLAB. Okay, so I have a program that creates a sawtooth, and I'm going to go ahead and run it here. This is going to create a 500 point signal, 500 time points. It'll complete 25 cycles. Okay, and let's go ahead and plot that signal. Oops, wrong one, sorry. Okay, this is that signal that I've created. We're not going to count them, but hopefully you believe that there are 25 cycles there. Okay. It is set for a total recording time of 50 seconds, which isn't really going to matter that much to us, but that's what we have. Okay. So this completes 25 full cycles over the recording period. Okay. All right. So now let's look at the Fourier transform of that. Magnitude. And this is what we see. Okay. So basically there is no content until we get to this point, which is MATLAB index 26, subtract 1, that means 25 cycles for the whole recording period, which is what we set that sawtooth to be. So we have content there, that's the fundamental, okay? The next one we see is at MATLAB index 51, which is going to be frequency 50 cycles per recording period. So that's 2 times the frequency of the fundamental. Some people would call this the first harmonic. Some people might call it the second harmonic. Just depends. But that's it. That's a harmonic. Okay, it's 2 times the frequency of the fundamental. The next one, you might guess, is at 75. Well, 76, but we subtract 1 from MATLAB. 75, the next one should be at 101. Subtract 1, that's 4 times the fundamental. There is not one at the next position. There's no content there. That has to do with the shape of the wave form. But if this was a different wave shape, there would be one there. And then we have one at 151. 176, 201, and so on. Okay. So the Fourier transform of that periodic signal only gives us content at these discrete frequencies, the same frequency as the original signal, 25 cycles over the recording period, and then integer multiples of that. We can do a second example. We'll do it for 10 cycles. Okay, so now this is a lower frequency, right? It completes 10 cycles in the recording period. And if we look at his FFT, fundamental at what? MATLAB index 11, minus 1 is 10. And then the next one should be at MATLAB 21, right? 2 times 10 plus 1, and 31, and 41. The missing one at 51, and then 61, 71, 81, etc. Okay. Now, the relative heights of these things are going to determine the shape of the wave within one period. Okay, so the relative heights of those, have to do with the sawtooth shape. If we had a different shape to our waveform, we would get different relative heights, but if it was the same frequency, we would still get content only in the same places, right? The fundamental and integer multiples of that. So this is important. This is going to come up a couple of times as we talk about periodic signals. And of course, in biomedical signal processing, there are lots of periodic signals or approximately periodic signals because a lot of biological processes do that, right? Heartbeats, etc. And so we will continue to look at that further as we go along. Thank you.